Here I have two sequences, and these two sequences are special. Why? To find out why, we're going to need to find the nth term form of a sequence, or it's also called the general term, general form. So let's do that by looking at this first sequence here on the left. A1 equals -8, A2 equals -3, A3 equals 2, A4 equals 7, and A5 equals 12. So as we go from -8 to -3, then -3 to 2, and so on, what's the pattern? If we go from -8 to -3, if we add 5 here and go from -3 to 2, that's also an addition of 5, and then an addition of 5. And so you see that the pattern works here, that all we're going to do is add 5 each time, and that gives us the next one. Well, I can write that in a slightly different way here. Let me write it like this. A1 is where we start. A2, however, is -8 plus 5. A3 is -8 plus 10, because we added 5 twice. But I'm going to write this, instead of writing it as plus 10, I'm going to write it as 5 times 2. 7 is -8 plus 15, or 5 times 3. 12 is -8 plus 5 times 4. Kind of going backwards, we can see that A2 is going to be 5 times 1. And then, of course, -8 is 5 times 0. And I wrote it this way because now we have -8 in each one of the terms, and we also have 5 in each one of the terms. And so those are kind of constants throughout this entire sequence. And what's changing here is this number in each one of these terms. And if you'll notice, these are all just the term minus 1, the nth term minus 1. This is 2 minus 1 is 1. 3 minus 1 is 2. So all we're doing there is taking n minus 1. What I can say then is, to find the nth term, we take -8, which -8 is just A1. So we take A1 plus this 5 here. Now, what do we call this 5? Well, as we go from A1 to A2, all we're doing is we're adding 5. A2 to A3, we're adding 5 again. And so it's like this additional thing here. We can also think of it as A2 minus A1 is 5. A3 minus A2 is 5. -3 minus 8 minus -8 is 5. 2 minus -3 is 5. And so on and so forth. And so we call this a common difference, D equals 5. So I'm going to write D here for that. Okay. And then D is multiplying by n minus 1. At this first term here, that was 1 minus 1 is 0. The next one was 2 minus 1 is 1. 3 minus 1 is 2, and so on. And this right here is the general form for what's called an arithmetic sequence. And it's an arithmetic sequence because it has this common difference. All you do is you add a certain number or subtract a certain number to find the next term. Okay, let's look at this a little bit more and try and figure out, why is this, is there something more special about this? And there is. I'm going to take all of these terms, so A1 equals -8, A2 equals -3. I'm going to take all of these, and I'm going to think of it as coordinate pairs. Namely, A1 is 1, -8. A2 is 2, -3. A3 would be 2, and so on. If I do that for all 5 of these, I can create this little graph here. And I've created a line to kind of go through it because it follows this trend. So this right here, this is just A1. This is A2, A3, A4, and A5. And it definitely looks like it's linear, right? It follows this line kind of straight through. Well, let's see if we can actually show that it's linear. Let's just look at this first one at A1. That coordinate is 1, 8. All right? Now, let's actually use the line here. Well, we can look and we can see that as we run 1 unit, this is just a run of 1 unit, we're going to rise from A1 to A2. We're going to rise 5 units. We run 1 unit. That means the slope, m, is 5/1, which of course is just 5. So we can use the point slope formula for this. And that gives us y minus y1 equals m times x minus x1. Plugging in our point, which is 1, 8, and our slope 5 gives us y minus, this is -8 here, not positive 8. Y minus -8 equals 5 times x minus 1. And that becomes y plus 8 equals 5 times x minus 1. Now this looks very close to what we can get when we plug in the things here, right? an equals -8 plus 5 n minus 1. A1 was -8 and D was 5 for our formula. Well, all we have to do is just subtract 8 to both sides. And now we see we get y equals -8 plus 5 x minus 1. And so these two are nearly identical. an equals y. A1 equaled -8. D is the slope. D equals n with the slope, which was 5. And then n equaled x. So an arithmetic series is just a linear function, but it doesn't contain all of the points in it as a linear function does. It contains only the integer values 1, 2, 3, 4, 5 for the x values. So there is some caveats, right? The linear function would contain everything on this line, this blue line here, everything on this, but our sequence only contains these 5 points. Well, it contains infinitely many, but these 5 points here. Okay, let's look at the next sequence here. So we have 4/3, 4, 12, 36, and 108. So A1 equals 4/3, A2 equals 4, A3 equals 12, A4 equals 36, and A5 equals 108. Okay, let's consider these things and try and see the pattern here, right? From 4/3 to 4, this is actually a multiplication of 4. Sorry, not 4, 3. 4 times 3 is 12. 12 times 3 is 36. And of course, 36 times 3 is 108. And so let me write this in a different way. Let me write this as 4 equals 4/3 times 3. 12 is 4/3 times 9 or 3 squared. 36 is 4/3 times 3 cubed. And 108 is 4/3 times 3 to the 4th. So now we can go backwards and fill in the rest of it. A2 is 4, which is 4/3 times 3 to the 1. And of course, A1 is 4/3 times 3 to the 0. And so you see we have the same kind of pattern that the arithmetic series had. And so now we can find the nth term here as being A1, which was 4/3. 4/3 was just A1. Then we have this 3 here in each one of these things. This 3, because it's a multiplication, it's called the common ratio. Sometimes you can multiply by fractions instead, and those would be more like ratios. But it's called the common ratio, and that's given the symbol R times R. And then once again, we have this power here. Just like in the previous one where we had these 0, 1, 2, 3, and 4. We have 0, 1, 2, 3, and 4, which is just n minus 1. We have r to the power of n minus 1. And for our function here, we have an equals 4/3 times 3 to the n minus 1. And this is called a geometric sequence. This is the general form of a geometric sequence here. And so we can use the same kind of process that we did with the previous one. We can plot these guys out. And what you'll notice is that it follows this exponential growth pattern, which is to be expected because we're multiplying by something each time. And so a geometric sequence is actually similar to an exponential function. It doesn't have every single value in the domain, just the integer values, but it does follow the same trend. Okay, we can show this quite simply by taking the same kind of ideas for the linear function here and plugging them into our general term. This really becomes y equals a1 times r to the x minus 1. It's a type of a function as a exponential function, where r is the base of the exponential function and a1 is kind of like the starting point, the starting adjustment. Okay, so now that we've talked about arithmetic and geometric sequences, let's talk about these two things as a series. So a series, right, we're adding up the terms to get to a certain point. Now here for this arithmetic series, -8 to -3 to 2 to 7 to 12. Let's take that guy and look at it a little bit. Let's rewrite it down here. 7, 12, and on up. This being an arithmetic series, right? If we took the sum of all these terms, well, it just keeps going on indefinitely, and it keeps getting higher and higher and higher. And so the infinite sum of this would just be infinity. And you'll either get plus or minus infinity for an arithmetic series if you take an infinite sum. So to find any kind of series for this, any kind of value that's interesting, we have to look at a partial sum or a portion of the series. So let's take this thing and let's look at what is the sum of the first 50 terms. So what we can do is we can actually, find all 50 terms by following the same pattern, right? This would be, next one would be 17, then we have 22, then 27, then 32. and find all of them and then add them all up, but that would take a very long time. So we should always ask, is there a faster way? And there actually is. We have this formula here. And this finds a partial sum of an arithmetic series. This actually isn't too hard to prove. I suggest you try and look at why this is the case. I believe the first person to prove it was Gauss, a mathematician. I'm not sure when he was alive, but so we can use this formula to find the first 50 terms by just plugging in S50. So we need to know what is A1 and AN, namely the first term, which is -8, and AN is going to be A50. That's the last term that we're adding up. You can, of course, expand this sequence out to find the last term, or we can use the nth term formula that we found previously, or the general form is also what it's called. This guy right here. This finds any term in the sequence that we want to find. So A50 is A1 plus D times 50 minus 1. Okay. This is going to be A1 plus D times 50 minus 1. A1 is -8. D, well, this is just the common difference. We have 5 each time. And then we get 49 here. -8 plus 5 times 49 is 245. And of course, adding 8 onto that gives us 237. So A1 is -8. And AN is 237. And now we just need to solve this arithmetic. -8 plus 237, that's going to be 229. And these two multiplied give us 5725. And so that's the sum of the first 50 terms for this arithmetic sequence. All right, let's look at another one. We want the sum of the first 80 even integers. Okay, where do we start here? Well, what might help is to actually write out a sequence for this thing. So the first 80, I should say this has a positive even integers. So the first positive even integer is 2, then 4, 6, 8, 10, 12, and so on and so forth. So to find the sum of these things, of the first 80 positive even integers, we can use this formula, plus AN. We know what N is just 80. We know what A1 is, that's 2. And the question is, what is AN, or A of 80? A of 80 equals, it's going to be A1, I'm just going to use this formula here, AN equals A1 plus D times N minus 1. A80 is going to be 2 plus, what's the common difference here? To go from 2 to 4, we add 2. To go from 4 to 6, we add 2, add 2. So every single time we're just adding 2. The common difference then is 2. And then N minus 1 is 80 minus 1. We get 2 plus 2 times 79 gives us 2 plus 1, 58. And so A80 equals 160. So now we can take this formula and plug in, the sum of the first 80 positive even integers is going to be 80 over 2 times 2 plus 160. 40 times 162, which equals 6480. Okay, and that's how we find a partial sum for an arithmetic series. So let's look at a geometric series now. A geometric series, especially the one we had in the first place, let me write it down again. 4/3, 4, 12, 36, and 108. Right, the infinite sum of this guy would end up going to positive infinity. So we have kind of a similar problem as the arithmetic series. So we need to know, is there a formula to find a partial sum? And there is. The nice thing about this formula is that we do not need to know the last term that we're adding up to. We only need to know what is the first term, and A1, and what is the common ratio R. So if you wanted to find what is the sum of the first 12 terms in this sequence that we have, we need to know what is A1. Well, that just equals 4/3. And what is R? And the R is just the common ratio. You multiply by 3, multiply by 3, multiply by 3, and so on. So R is going to be 3. So the sum of the first 12 terms of this wouldn't be too hard to calculate by hand, by just continuing the sequence so that you have the first 12 terms. But we can use this formula to find it much faster. It's going to be 3 to the 12 over 1 minus 3. So we have 4/3. 3 to the 12. It's a big number. I'm going to do 1 minus that. Is negative 5314440 over negative 2. And I'll just multiply all those together. What gives that? 354,293, and this is 0.3 repeating, which is the same thing as 1/3, and that comes from the fact that A1 has a decimal in there. So we have this as the sum of the first 12 terms of the sequence. Not too hard to work with. This can sometimes be, long numbers because we have this whole portion of it. But just keep that in mind when you're working with it. Let's look at another one. So here's the next one we're going to look at. And now this is a partial sum by definition, right? We're summing up only 7 terms. But this doesn't look necessarily in the general form of a geometric sequence. It's a little bit weird. What we can do, we can find what we need to find quite simply by just expanding this sum. So I'm going to plug j equal to 1 into here, and that gives us 3 times negative 2 times to the power of 1. And then j equal to 2, then j equal to 3. And we don't need to find actually the rest of them. So 3 times negative 2 to the 1 power is going to be negative 6. Then we have 3 times negative 2 squared. That's going to be 4. So 3 times 4 is 12. Then we have 3 times negative 8. That would be negative 24. So I'm going to write a negative there. And so on for the next 4 terms in the series. Now what's interesting is that this one is an alternating series. We have negative 6 plus 12 minus 24 plus something next. That doesn't matter, however, we can still use the formula that we had for geometric series, namely 1 minus r to the n over 1 minus r. As long as we encode the right information, this formula will still work even though it's an alternating. And that formula, or that correct encoding the right information, happens with how do we go from -6 to +12? What are we multiplying by? We're multiplying by -2. And to go from +12 to -24, that's again a multiplication by -2. And so r here, r is -2. And that's what makes it alternating. And we also know A1 is just the first term in the sequence, which is going to be 6. So to find the first 7 terms, right, j goes from 1 up to 7. So we're finding the first 7 terms. We're going to do the sum 7 equals A1, which is -6, 1 minus r to the n power, all over 1 minus r. We get -6 times 2 to the 7 is 128, and then that's going to be negative, so negative and negative is positive, so we get 1 plus 128 becomes 129. These two negatives cancel, and we get 3 on the bottom. Of course, that reduces with that to 2. And we get negative 129 times 2 is 258. So the sum of the first 7 terms in this series, and there's actually only 7 terms because it doesn't continue on. You could, however, continue the geometric sequence if you wanted to, but to find this actual sum, this is how we can do it. I would expand it, find what r is, find what A1 is, and go from there. Now, geometric sequences are unique from arithmetic sequences, and I'll show you why. Let's look at this geometric sequence here. (16), 1 over 64, and so on. So how are we going from the first term to the next one? We're doing 1, and then we are dividing by 4. Now, a geometric series or a geometric sequence does not do division, it does multiplication. The question is, how do we write this thing as a multiplication? Well, division by 4 is the same thing as a multiplication by 1/4. We're going to multiply by 1/4 instead. So here we're going to multiply by 1/4, multiply by 1/4. And so what we have here is r equals 1/4. Now, where does this thing go if we were to add up all of these terms? Well, where do the actual terms go? Like, we go from 1 to 1/4 to 1/16 to 1/64. It goes, and eventually, right, if it goes on off to infinity, it'll go to 0. And so this term here, this sum gets smaller and smaller. We're adding smaller and smaller pieces to it. And so eventually we get such a small piece, we wonder, does this actually end up adding to infinity? And this does not. As long as we have this rule here, -1 is less than r is less than 1. It's saying r is between -1 and 1. It cannot equal those, but it can be less than 1 and greater than -1. As long as we have that, we can actually find an infinite sum of a geometric series. What's even more interesting about this is that the formula for finding this, instead of using Sn, we just use S because it's the full series. This formula is quite simple. It's just A1 over 1 minus R. So plugging in the information we had, right? A1 equals 1 here. That's the first term in our sequence. we have 1 over 1 minus 1/4. We get 1 over 3/4, which is 4/3. So if we were to actually do this summation here, it goes to 4/3. It doesn't go any higher. It only goes to 4/3.